Okay, introducing the Taylor and Maclaurin series. Taylor and Maclaurin series as a way of writing down a power series. Here is an example of a power series. It's one that involves powers of x. And x squared is the highest power of x, quadratic in other words. It may have a term of x and it might have a constant. A cubic might have a term involving x cubed, a term involving x squared, a term involving x, and so on. So a power series is something that we can express a function as. A function can be expressed as a power series. And we say that if this is the case, then we write down that fx, the function fx, might well consist of a constant, c, let's call that c0, and then a term involving x with a coefficient, let's call that c1, a term involving x squared with a coefficient in front of it called c2, and so on. If this function can be expressed as a power series, then one condition is that the function must exist at the point we're considering. So, for example, if we look at this function, the function y equals log x, we can see that when x equals 0 around about this point here, then the function disappears off to negative infinity. The function does not exist when x equals 0. So we can't consider the function around point x equals 0, but we could consider it around other points. Here, for example. So long as the function exists at the point we're considering, then we can represent it as a power function. So if we consider some point A where the power series exists, we can write that the function may have some constant in front of it, some coefficient c1 multiplied by x minus a. So we're considering values of x now beyond the point A that we know that p exists at. And so on. c2, x minus a squared, x minus a to the 4 cubed, and so on. And so again, get the general term cn x minus a to the n, where n is some power, and you can see the suffix by the c gives us that coefficient. So that's the general term. So we're saying that the series must exist at the point A, and then we're going to assume that we can write any function fx in some sort of power series form. All we've got to do is find out what the values of these constants are, c0, c1, c2, and so on. We also have the condition that the series must converge. So as we go along, these terms must get smaller and smaller and smaller. If you think about it, if the terms got bigger and bigger and bigger, then there's no way we could ever end. When we get to the infinite term, that would be an infinite value. So we can't express a function in terms of a power series if it diverges. So the series must converge, and we need to be able to find out whether it converges or not. So we'll talk about that a little bit later on. And if it exists as a power series, in other words, we've got all these terms, then if you think about it, we must be able to differentiate it. If you look at this power series, if I differentiate it, this term's going to disappear because that's a constant, and then we'll just be left with c1 because the x term will disappear. This 2 will come down and go in front, and then the 3 will come down and go in front, and we'll change that power to 2. Then if we differentiated it again, other terms will disappear, and again and again. If you think of this nth term here, we can differentiate that n times. Or, if n tends to infinity, we can differentiate this power series as many times as we want. So, in other words, if a power series exists, we must be able to find this nth derivative. So we can differentiate this power series as often as we like. And we'll see that that's an invaluable way of finding out what these coefficients are in front of each of these terms. Okay, so the best thing now is to have a look at an example of how we can use this idea and how we end up with Taylor series, a way of finding these coefficients in front.